Sir, is the derivation we discussed in last class important from exam perspective?
Yes, it is. So you should know the derivation. Yes. Okay, so okay, so in the last class, so we were discussing about anti-reflection coating, where we have a so for any material surface. For example, here is, let's say, glass, and you want to coat the surface, so you want to reduce the reflection from the surface. So you can coat the surface with a material having a refractive index NF. Let's say this is a thin film that you are coating on top of the glass surface. So this is your Ng, is your refractive index of glass, and let's say D is the thickness of the coating, and Na, so which is equal to 1, is the refractive index of air. And using the Maxwell's formalism, so we calculated the reflectivity or reflectance from the surface is given by, so R1 square plus R2 square plus 2 R1 R2 cosine of 2 delta divided by 1 plus R1 square R2 square plus 2 R1 R2 cosine 2 delta. And what is R1? R1 is equal to reflection coefficient from the top surface, air and the film interface, Na plus Nf, and R2 is the reflection coefficient from the film and glass surface, so which you write as Nf minus Mg divided by Nf plus Mg. Now, the phase difference that you introduce in this system, the phase difference delta, so this is what appears in the reflectance. So delta is nothing but your 2 pi by lambda into the the path difference, Nf by d. So this is the path difference that you have introduced, and this is related to the phase difference that appears when the wave is reflected from the top surface from here. So this is one reflection, and then there is another reflection from the interface. Okay, so to minimize this reflection, so you want to have a destructive interference, and that would happen when your cosine of 2 delta is equal to -1. And that means your reflectance would be, you can write it down as R1 minus R2 by 1 minus R1 R2 whole square, which you can now replacing these values of R1 and R2, so you will get an expression NaNg minus Nf square divided by NaNg plus Nf square whole square. And so if you want no reflection at all, the ideal situation when you want R should be equal to 0, so in that case your Na into Ng would be equal to Nf square. That means your Nf, the refractive index of the film, should be square root of Na and Ng. So if you take a glass and air, so the film should have ideally a refractive index of 1.222. Now, the other condition, that's the destructive interference, means the path difference should be cosine 2 delta is -1. That means the path, the phase difference is odd multiple of pi. So where, right, m is equal to 0, 1, 2, and so on. So this is an odd multiple of pi. And so that implies, so if you now want to calculate what should be the optimum thickness, so you can calculate that. So it will be now replacing delta by the path difference. So this is will be equal to 2m plus 1 pi, and which means your d, the value of d should be equal to 2m plus 1 lambda by 4 nf. So which is again should have the values for nf, 3 lambda by 4 nf, 5 lambda by 4 nf, and so on. So this is the optimized thickness and the refractive index that you would need in order to make the coating anti-reflection coating. So now what happens if your film refractive index of the film is higher than that of the glass? So let's say we have a situation where now this is the glass I have, and I have the coating here. Now this NF is greater than NG. So for minimizing the reflection, we saw that NF, so here we saw that NF, this value of, yes, yeah, so NF should be square root of NA into NG. And that means, so typically the value should be around 1.22, okay? So if you take such a material, such a coating, so you would get an anti-reflection coating. But what happens if the refractive index is higher than the refractive index of glass? So in that case, this cosine 2 delta, so keeping everything the same, this condition would lead to actually a maxima. So the interference condition would change because of this additional phase change at the so there is no phase change at the film and the glass interface, but there is only a phase change from the air and film interface. So due to this difference, so the condition will change. So you will have a maxima. So that means you are having a constructive interference. So that means you can make a surface more reflecting. Okay, so you can also do that by just changing the refractive index of the coating. So if you want to make your glass more reflecting, so you can have a coating with a material which has a higher refractive index. So for example, so zinc sulfide coating normally people have done where this refractive index is about 2.37, and you can actually achieve to increase the reflectance by 33%. So you can substitute the value, so you can calculate R1 and R2. So all the calculation will remain same. You can substitute, so you can start with this equation now. So but condition remains the same. Cosine 2 delta is still -1. So this equation, so you can use this R1 minus R2 by 1 minus R1 R2 whole square, and in that case R1 and R2 will change because NF has changed. And if you do that, so you will get so for air, just normal air and glass interface, so we calculated the so 4% will, the reflectivity will be 4% of the incident wave. So 4% of that amplitude will be reflected back. But if you coat with the zinc sulfide, so you can increase the reflectivity by 33%. So I will pose a question here, so which I also don't have an answer to, so which probably will lead to some, so there is scope. Definitely, people are working on this direction actually. So the question is, uh, so can we have a coating where we can vary or change the refractive index, and we can make it more reflective or less reflective depending on the application. So we have the same kind of coating, so we are not changing anything. So here what you observe is we have to really make another coating to change the reflectivity. Okay, so to make reduce the reflectivity, you coat MgF2, so magnesium fluoride, for example, which has a lower refractive index, and to increase. So for example, here we are coating with a higher refractive index. But is it possible to change or vary in such a way that you make the surface more reflecting or less reflecting as per the application? So that you have the same coating, so you are not changing anything, but you devise a way uh, which will help you in changing or varying the refractive index depending on the application that you are looking at. So that will be more like a universal coating that you have, and by some means you can change this n. So there are people working in this direction, so you can look it up. And so if you are interested in future, you can also bring some innovation in this direction. So these are very, so I can give you one example here. So this is like in airplanes. So aeroplanes, so when you have the windows, so normally what you want is you want to change. So depending on the outside, whether it is bright or dark, so you want to make your window darker, or so what you want is you want more light to pass through or less light pass through. So depending on, so let's say if it is a, yes, it's kind of that, this sun shield that is being used. So these are again in the high-end technology that is being used. So can you make it more, so this innovation which you can bring to like make it cheaper and make it available to everyone. So that would be a great innovation. So this sun shield that you have mentioned, and so this is actually used in many cases, and there are a lot of scope in this direction in future. Okay. So one question is, so when we are saying, let's say this that we have an anti-reflection coating, for example, that means the so we are having a destructive interference and we have no reflection. So what happens to the energy in that case? So we have an incident light with certain energy. So what happens to the energy in that case? If we are saying we have a destructive interference, so what happens to the energy that is carried by the light?
So is it absorbed by the material?
Okay, one possibility, it can be absorbed. Okay, any other?
It increases the heat of material.
Yes, indirectly, that is what the absorption would do eventually. So if the energy is absorbed by the material, so it would eventually heat it up. Yes, that is one possibility. Also, that is of course one possibility. Another possibility is it's getting through the transmitted wave. So, so the energy that is lost due to this destructive interference will go to the will be so if the material is not absorbing, so it will go through the will be carried by the transmitted wave. Okay, so there are two examples which you probably would you might have seen already, that use this interference pattern of this film. Okay, so this is like one application, but there are also certain example where you can see how the interference manifests in a film that it's trapped in such like these thin film systems. Okay, so one example I think you probably would have seen or have already know about it. So one is the fringe pattern that is observed in air film uh, trapped between two glass plates. Okay, so if you take two glass plates and then you uh, put them together face to face, now it is possible that there will be some air film that will be created within the two surfaces, and that is because your surfaces might not be perfectly flat. So if it is not perfectly flat, so you can have some air pockets, and that would actually also form a kind of thin film air film which will create a fringe pattern, which can be described by all this what we did these calculations. So another experiment is a Newton's ring experiment. So this experiment, I will, so it is explained in the book, quite easy to understand. I will leave it because this experiment you will be doing in the uh, in physics lab. So when you come to the campus to perform the physics lab, you will be performing this one of this experiment, Newton's ring experiment, where you will observe this interference pattern uh, due to a air film that is trapped between a glass plate and a plano-convex lens. So you have a very special convex lens known as the plano-convex lens, and then a flat glass plate. And what will be the fringe pattern due to that, you will perform that experiment that is known as Newton's ring. Okay. Another very useful so we cannot say it's an application, but the use of interference pattern is the Michelson interferometer. So have you heard about this name? Michelson interferometer?
No, sir.
No? Okay. Okay, so what is this Michelson interferometer does? Before going into that, so I will give you two examples how this interferometer has helped physics in general, to understanding of general physics. So, so the first experiment actually, so this interferometer was developed by, of course, Michelson, and he performed one experiment together with Morley, Michelson-Morley experiment, uh, which actually led to prove or disprove that ether doesn't exist. So the first experiment, experiment one, using this Michelson interferometer, proved that ether doesn't exist, because in when Maxwell proposed his electromagnetic theory, so at that time everyone thought yes, any wave need a medium to propagate. Okay, so there is no way electromagnetic, I mean your electromagnetic wave can move without any medium, and people believed that ether, which surrounds everywhere, all the space around us, so it is occupied by or filled by ether, and electromagnetic wave propagates through ether, this medium. And to prove that, actually, Michelson and Merle, they did an experiment uh, to show that, yes, so I will present the interferometer, and you can read the Michelson-Morley experiment, uh, very nicely described in this book or any source. Very one classic example of this use of this Michelson interferometer. So proved that ether doesn't exist, and it led to the special theory of relativity by Einstein. Okay, so this led to the special theory of relativity, which basically tells you that your space and time are not independent, so they are so you represent the motion of any particle or any mass as a function of your space and time always. And also it led to the famous equation E equal to mc square. So energy, so you can transfer energy and mass, so they are related by this equation E is equal to mc square. So this experiment actually proved very, so in that way it is a profound experiment which was done by Michelson, and it proved that ether doesn't exist. So you can read about this Michelson Morley experiment. Uh, and then the second this, oh yeah, okay. The second experiment, which is more recent one. So there are many other experiments which are based on this Michelson interferometer, which helps in other fields. But two examples I'm giving here to show that how profound this experiment in context of physics. So the first one done, I think in 1880 or around 1890, so late 20th century. And the second experiment is really a recent experiment, which is known as, short form is LIGO. So it stands for Laser Interferometer Gravitational Wave Observatory. So where they use the same principle here as proposed by Michelson. So it is again a Michelson interferometer, where they proved that gravitational wave exist. So I will share a couple of videos regarding this LIGO experiment, so you will understand what is the gravitational waves. They exist, and this actually proved Einstein's general theory of relativity. So two experiments. So this LIGO experiment was, I think, this confirmation of existence of gravitational wave was done in 1916, I guess, 1915 September or 1916, around that time. So very recently, and this showed that gravitational wave exists, which Einstein proposed in general theory of relativity, which was not, so it was a hypothesis until that time. So that's why this experiment is really very interesting from physics point of view. And what is the experiment? So let me show that, and then we'll okay. So what you have, how do you perform this experiment? It is again a very interesting way. So let's say you have a source here, and this is, let's say, your point P, from where so you put a pinhole or something like that. So this, you can say, this is from where your wave originates from, point P. Now it travels, and what you put is a something known as a beam splitter. So this is glass, this is known as a beam splitter. So what it does, so it splits the beam, so partially it will be reflected and partially it will be transmitted. So let's look at the first the reflected one. So this is partially reflected, and what Michelson did, he put a mirror here, M1, let's say. So now this is reflected, so this, let's call this 1. Now if you put a mirror, so this beam will again will be reflected back. Okay, so this we call 2, and then it will be partially reflected in this direction, and then it will be transmitted along this direction. So this so sorry, we call this 1, this is 3, and this is 5. So the number, you will understand why I'm doing that. So first partially reflected 1, then again it is reflected from a mirror M1, and then transmitted to the beam splitter, which I call beam 5. Now again the initial beam, there will be a partially transmitted one, so let's call it 2. Then he put another mirror here, so this is again, it will reflect back. Okay, so when this reflects back, so this, let's call it 4, and then from the beam splitter, this one will also be reflected in this direction, also partially will be transmitted in this direction. So this we call 6. And now if I look here, so I will have an interference pattern. Okay, so because these two beams are coherent and they will interfere depending on the path difference, because they are traveling in different directions, so there is definitely a path difference, and that will lead to a interference pattern. So this is the basic setup of Michelson. You can produce, so this is another way of producing interference pattern. So now if you what is the path difference between the beams? So if you actually look at these 5, and this is, let's say, called 6, so it would appear from this direction. So if you are looking from this direction, so it would appear as if the beam, so 5 is coming from the mirror 1, and the 6, number 6, this one would appear to come from, so let me use another color. So this 6 would appear to come from a mirror, which is a virtual mirror. So this is our M2, let's say. So this is a virtual mirror M2 prime, from which this 6, the beam is coming. And so what would be the path difference? So the path difference is nothing but the distance between these two mirrors, M1 and M2 prime. And M2 prime is like a virtual representation of mirror M2. So if we know what is the distance of mirror M1, so if we say this is x1 and this distance is x2, so your distance would be equal to x1 minus x2. And that means the path difference is 2 times d, because the beam goes, so travels here and comes back, so it travels a path difference of 2d. So let me, because I wanted to, yes, so this is, I will show it later. Oh, sorry. So let me put a here. Yeah. So this is a representation of that here from the book from Ghatak. So it's a schematic representation of that, and the interference pattern, which typically you will observe this circular fringe patterns. Okay, and the condition for interference pattern is, again, we know the path difference, and this is will be your constructive, and if it is m plus half lambda, this is your destructive. So m will be your integer. So what is theta here? Theta is nothing but this angle that you see the fringe pattern will make with respect to your central axis. So this is your central axis, and this is your theta. Okay, because your this path difference depends on this 2D cosine theta, which depends on at what point. So p, which point you are looking at on the screen. So the consequence is, so if you increase d, basically what would happen that the fringe, they basically will collapse and move towards the center. And if you increase or if you decrease d, so the fringe will actually collapse and they move more towards the center. And if you increase d, so you expand the rings. So this is what happens. And this figure, from this figure, it will be clear. So let's see, where is that? Oh, I put it too far away. Okay, so here this is a experiment which shows the dependence of the fringe, how they change as you change d. So now if x1 is equal to x2, exactly they are at the same distance from the beam splitter. So that means d will be equal to 0. In that case, there will be no interference pattern. So you will see just a dark green, that's all. Now we have increased and we go to this d is equal to something around 0.14985 millimeter. So they have certain number. I don't know why they use this number. So I think it is about 150 micron. Okay, so that's why they are using it. Yeah. So 150 plus minus something like that. So this is 149.85 micrometer. So here you see, immediately you see a fringe, this interference pattern. Now look at this, the other one, this one, d is equal to 0.15, this one now. So what you see clearly, you see the central part is here bright, but here the central part is dark. Okay, so by changing a little bit, so you have changed d by 0.15 micrometer. Okay, so really small change in d would change the fringe pattern completely. Okay, and what else you observe, one thing by increasing, so here it is not that evident, but one thing is clear, that you change the pattern if you change the distance d between the mirrors. Okay, so basically if you change the x1 and x2, you will change this interference pattern. So now this is for d is equal to 0.3 millimeter, so it is about 300 micrometer. So if the separation now you increase to 300 micrometer, so you see very similar to what you have as 150, but you see more number of rings. Okay, so the density, the number of rings within this area has increased. So that means in a way you say that the rings are actually expanding. Okay, so you have more and more rings that come out from the central part. And this is because you satisfy this, if you look at this value m will be different depending on the d. So whether how many fringes you will observe, so the density, the number of fringes will change because of that. Okay, so how this is then what is any use of this? So Michelson, so one, as I saw that, so you can perform this experiment to understand actually if your interferometer is stable or not. So that means if there is any change in D due to some external disturbance. So the disturbance can be due to a ether, so-called ether, which was imaginary, or if it is due to a gravitational wave, or due to your any sound wave you are producing, or any mechanical wave that you produce. So if that disturbs this D, so you can actually see a change in the fringe pattern. So now if you are very sensitive with your micrometer scale, which you can observe this fringe pattern, change in fringe pattern, so you can actually detect whether there is an external disturbance or not. And you can then calculate the wavelength of that external disturbance. How? So it is very easy. So if I look at only the central fringe, let's say, so not the other rings, only at the central fringe. So I can say for central fringe, theta is equal to 0. So in that case, my condition is 2D is equal to m lambda for the maxima. Now, if I move the mirror by a distance d0, so move mirror by d0, okay. So what would happen? So there will be, so if I increase, let's say to or decrease to d0, so that means some number of fringes will collapse to the center, so that the density will decrease. So you can calculate how many fringes are collapsing into the central fringe by using a micrometer, like a microscope with has a micrometer scale in that. So let's say n fringes collapse to the center. Okay. So if you have a look at a central fringe, so you have the condition 2D is equal to m lambda. So now if you move the mirror by distance d0, decrease the distance, so n fringes will collapse. So in that case, your 2d0 would be equal to so now you are decreasing it by d0, so the distance is d minus d0, okay, and this integer will be m minus n into lambda, because n number of fringes has collapsed. So this, if you subtract this equation from the first equation, so by subtraction, so what would you get? You'll get 2d0 equal to n lambda, or you can say your lambda will be equal to 2d0 by n. So you can calculate what is the wavelength of the light that is causing the interference. If you know what is d0, how much, so you don't need to really know what is the exact distance of the mirror from the beam splitter, but what you want to know is the separation between the mirrors. So if you change the separation by d0 and you observe that n fringes are collapsing, so you can calculate lambda. So this is a way you can calculate the wavelength of the wave that causes the interference. Okay, so this is actually is used. So now if you change, if you have any external disturbance, as I said, it can be a mechanical wave or anything, okay, which will change d, it will automatically, so it will basically change the shift, this d0, and you will observe a shift in n, and then you know what it is due to the gravitational wave. So then you can, or in a LIGO experiment, that is what was done. So it was related to the gravitational wave. So I will share some video regarding that, so it will be clear about this how LIGO experiment, because it's a very beautiful experiment and a recent example of how interferometer are so useful, which are based on laser. Okay. So another thing which I will just partially mention here is that you can also achieve a interference by multiple beams. So using a multiple beam, so far what we saw, that only two beams, we are using two beams produced in many different ways by dividing the wavefront, by dividing the amplitude. Okay. But you can also divide the amplitude and produce a multiple beam interference, where this is, let's say, a glass surface. So you have one wave like this, and then a transmitted wave, so which is partially reflected from here, something like this. Again, this one will also be reflected back, reflected from this one, and then transmitted, and so on. So there are multiple beams and amplitudes that are available which can interfere as well, which can also lead to a interference pattern. And one example here is the, I will show here, so which is known as the Fabry Perot Italo. Okay, so this is a special kind of application of that multiple beam interference. So what you have is basically a source, and then you have two glass plates which are partially reflective, and the separation is H. So this is the separation H, and you will observe a fringe pattern due to this multiple beams that come out transmitted from the this etalon. Okay, so this is has also some applications. For example, you can look at the flatness of the coating. So in such a device, so you can actually calculate how flatness. So if you put any optical coating, so you can calculate what is the flatness of coating. You can actually also produce some you can call it, let's say, some spectral distribution of your incoming beam. So you can actually produce that as well. So like your splitting of spectral distribution. So that means your incoming wave has certain frequency nu, and then you distribute it into maybe so 5 spectral lines or 10 spectral lines depending on this H. Again, you will have a interference condition will be there, so all these will be satisfied. So we'll not go into the detail, just I want to give a idea that this is another way of producing interference pattern as well. Okay, so you can also use this Fabry-Perot as a, it's like also interferometer. So, but it is not really called a interferometer unless you vary this H. So when you vary this H, the distance between two glass plates, so in that case you call it a Fabry-Perot interferometer. So that again is a similar to your other interferometers, but the purpose is different. Okay. So far in the coherence, for the interference, we assume that your beam is coherent, right? So one condition we always say that beam should be coherent. So what it means? So one thing it means, there should be it should be monochromatic. Okay. So the beam should be monochromatic, and there should be a definite phase relation between two waves which are basically interfering. So if they are interfering, so there should be a definite or a constant phase difference. Either they should be the same phase or the phase difference should be constant. So there should be a definite phase relation between the waves, then only you will observe a interference pattern. But this is a very idealistic way of representing this coherence, because so if we say how do we understand this from the point of view of electric field? So if we say our wave is represented by this electric field, so we are still in the one-dimensional representation. So we say the wave, the electric field is represented by E equal to E naught cosine kx minus omega t plus phi. So this means it's like a sine wave or a cosine wave. Okay, so you can draw it like this, perfect cosine. Okay, so what it means? It means for any time, if you take for any time period, so if I say or at any point in space, so for any value of x, for any x, this this pattern is a follows a cosine function. Okay, so it is always cosine or a sinusoidal of wave. So it can be a sine wave or a cosine wave. So it is always like that at any point x and for any time t. So if I say my time is between plus minus infinity for any point in space x, so this is a cosine wave. But it cannot be true always, because the process of producing this electromagnetic wave is due to this transition in the electrons from one level to another level, and which can lead to it's like it can lead to a phase difference during the process. It may not be so definite. So it's more or less a random process, and therefore you may not get a perfect or ideal monochromatic wave which satisfies this condition or for all duration of time. So what actually happens? So the wave train that comes due to this de-excitation process, so may not be like this, always doesn't obey this cosine function. So there can be some discrepancies. Okay, so it can change for a certain time. Okay, so this distance, so let's say, so you see some kink or jump here at this point, and something happens here to the wave. So more or less it looks cosine, but there are some point in time. So this is, we are plotting as a function of time at certain time t. So there are some there is a difference here. So this tau, this time for which it remains in such a follows the cosine form, so this time is known as the coherence time of the wave. Okay, so this is the coherence time, or sometimes it is also called as tau c. Okay, so now, and that means for this, so what is the distance or the length that is traveled by the wave? So the distance L is c into tau c, which is known as the coherence length of the wave. So this is normally what happens for any wave, electromagnetic wave that comes from a source. Okay, so you have a certain time period over which the wave remains cosine like or sine like. So it's let's say a sinusoidal wave. So it remains sinusoidal for a length of time known as tau, which is the coherence time. So that means after that again there is some change, but again it goes back to a cosine wave and so on. So this, so what is the implication in terms of interference? So if you look at your double slit experiment, Young's double slit experiment. So this is your S1 and S2, and we say we are observing a interference pattern at P. Okay, so this is your optical path. This is R1 and R2. So at point P, in order to observe the interference pattern, you should have the difference R2 minus R1 should be equal to L or less than L. Okay, so it should be less than equal to L. If it is more than this coherence length, so that means the wave coming from S1 travels a distance R1, and if the difference is more than the coherence length, so in that case there will be no interference pattern. So only if R2 minus R1 is less than L, so you will observe a interference pattern. Okay, so in terms of tau, we can write it like so just divide by the velocity of light, which is R2 minus R1 by C, so which should be equal to less than equal to L by C, or it's equal to tau C. So if the path difference or the time difference between the wave that arriving at point P, if it is, so in that case we say this is the delta. Sorry. So delta T, that is equal to should be less than tau C. So if the delta T or the time when the wave from S1 arrives at P, and the time a wave arrives at point P, there the difference is delta T is greater than the coherence time, so then there will be no interference pattern. Okay, so this is the coherence time in context of Young's double slit experiment. So interference will happen, and if delta T is greater than Tc, so no interference. So this is true for any wave. So the typical, what is the typical value of this tau, this coherence time? So if you take a cadmium light or your sodium light, for example, so or cadmium light, it is about 10 to the power 9 minus 9 second, which gives rise to L of about 30 centimeter. Okay, so if the phase or the path difference is more than 30 centimeter, so in that case you will not observe any interference pattern if you are using a cadmium light. But if you are taking a laser like a helium neon laser, so in that case this tau is of the order of 50 nanosecond, and L, if you calculate, so multiply just C in tau C, so which will come out to be about 15 meter. So that's why it is really easy to observe interference pattern with really good contrast using laser light. Okay, so most of the experiments nowadays that you can actually also do that. No, nowadays lasers are very cheap. A laser pointer you can buy. So if you want to get a good high intense laser, so maybe you have to spend 500 rupees or 700 rupees, and you can buy a really nice laser pointer, and then you can do this experiment and see for slits which are far away, much larger than few meters, you may not observe the interference pattern. But that's why most of the times you want to put the slits as close as possible. Okay. So this is in the context of this double slit experiment, how coherence is defined. Okay. So you have to define the coherence. The wave will have a coherence time. So this is also known as a temporal coherence. So the beam has a temporal coherence, which translate into your coherence length, and that defines whether the interference pattern will occur or not. So this is also, one can do the same thing for the Michelson interferometer that we saw earlier, and in that case, so your the path difference is, so for Michelson interferometer, so your path difference 2D should be equal to your coherence length L, or your 2D by C should be. So ideally it should be less than your tau C. So then you will observe a interference pattern. Then there is another kind of coherence that also, so some of you mentioned in the, when we discussed about the Young's double slit experiment. So one consequence of this, you can actually derive that how monochromatic is your wave. So monochromatic means it should have a single wavelength. But most of the time you will see that your wavelength is not always like one value. So there can be a spread in the wavelength. The from the source that comes, the wave comes out. So it is not a lambda, but it is a lambda plus delta lambda. Okay. So this delta lambda is the spread in wavelength. Okay. And this is due to this temporal coherence nature of the wave. Okay. So in a context of Michelson interferometer, so you can say, like, if the wavelength, I mean, it is difficult to plot it, but normally this wavelength spread, you can say, this is, let's say I would call delta lambda. So I would expect that I should have only one lambda, but instead of that, I will have lambda plus maybe some. So this can be a continuous change. So it is not a discrete one. So although if you are looking at the transition, atomic transitions, so you will see maybe this sharp peaks, lambda 1, lambda 2, and so on, like in sodium light, for example. But what you get in most of the waves in laser or any typical sources, you get a spread in lambda. So it's a continuous spread. So that spread is normally given by delta lambda. So each, that means for each lambda plus delta lambda 1, delta lambda 2, and so on. Okay, so any value of lambda between lambda plus delta lambda. So, so that means your wave, or let's say to simplify it, so your wavelength of your light or your wave will be somewhere between lambda plus delta lambda. So for each lambda L of light, so there will be a condition for maxima and minima. Okay, and they have to satisfy this interference condition so that you get maxima and minima and so on. Now, if your delta lambda is more than half of lambda, this spread is more than half of lambda. So in that case, what would happen? So let's look at the interference in the Michelson interferometer. So we said 2D should be equal to m, let's say lambda 1 for interference, for a constructive interference. Okay. Now, if I change lambda 1 and in the spread, what you have, I have another wavelength which has lambda 1 plus half of lambda 1. So in that case, what would happen? So 2D will be equal to m plus half lambda 1, and that will lead to a minima. So in the same wave, I have a maxima as well as a wave which satisfies the condition for destructive interference as well. And therefore, I will not really observe any interference pattern in that case. So in order to observe an interference pattern, so it should be, the spread should be much less than this half of lambda 1. Okay, so this, so I'll not go into the detail. So what it means, you can write this delta lambda should be, so it is easy to do this calculation. So you can look it up in the book. So it will be the order of lambda square by L, or should be by of this. So if delta lambda is of this order, so then you will observe, or less than that, so you will observe an interference pattern. If your wave has a larger spread delta lambda, so then you may not observe an interference pattern as well. Okay, so this you can actually represent in terms of frequency normally. So you don't say spread in wavelength, but frequency, you know it is c by lambda. So your delta nu would be equal to c by lambda square divided by into delta lambda. So you can write what is delta nu by nu. You can write something like L by C, which is will be equal to 1 by tau. Oh, sorry, this will be, so if you substitute that, so you will get this will be proportional to 1 by tau C. Okay, so your this is a this will define the purity of your spectra. Okay, so this is a known as a spectral purity. Okay, so this is already time, so I'll stop here and then we'll continue in the next class. So the next class we will have a 2 hour long, so we will have the extra class as well. So from 11 to 1. Okay, and I will also conduct a quiz on Thursday. So at 12:45 we will have a quiz. So I'll
So
conduct
which
one.
topic?
So the first Thursday will be until what we have covered until last Friday. Okay.
Sir, only
And,
Okay.
optics.
Okay,
sorry,
sir.
optics part. Yes, only optics part.
Okay,
Whatever I
sir.
have done. So only optics part. So Thursday we will have one quiz, and then Friday I will have another quiz after the class. The Friday quiz will be from whatever we are covering from today until Friday.
How long will be the quiz?
Quiz will be all Google form based. So either like you answer in one word or one sentence, or maybe multiple choice. So maximum would be 10 minutes, not more than.
Okay, sir.
Okay.
Okay, sir.
Can you
Yeah.
repeat when is the
So Thursday I will take the quiz 12:45. So we will have a class because I want to take the extra class. So 11 will start until 12:45, and then we will have the quiz, and then Friday will be the next quiz. So after the class, 11 to 12, and then we'll have the next quiz. 12.
Okay, sir.
Okay.
Okay, sir.
Okay.
Sir, thank you, sir.
Because 20. I mean Friday would be the last class, no?
Yes, sir.
Yeah. Okay.
Yes, sir.
Yes. Yeah, your voice is breaking. Yes.
Sir, could you repeat the syllabus once again?
So syllabus for the Thursday quiz will be, we started from, so the optics we started until what I have covered until last Friday.
Yes,
Okay.
sir.
And for Friday's quiz, it is what we are covering, we'll cover this week basically.
Okay, sir. Thank you, sir.
Okay. Any other question?
So would the quiz be MCQ or written?
It will be in the Google form.